Lecture 10, Part 1. We will continue from the previous lecture about natural language processing and more importantly about generative models. And this time we will discuss a model called Bayesian Network. But before that, I want to first give a brief review about random variables and probabilities, in particular, multiple random variables. So the first important definition is the joint distribution between two random variables, two or more random variables. It's basically specifying the probability of these variables taking on some specific values at the same time. So suppose xj can be either 0, 1, or 2. Xj prime can be also 0, 1, or 2. Then given a specific value like xj is 0, xj prime is also 0, we need to specify a probability. That probability needs to be between 0 and 1. And the sum of all of these 9 possible events needs to be 1. So that's basically specifying in all 9 possible situations what is the probability of this thing happening. And given that, we can compute the marginal probability. So we can compute the probability of only one of them taking on a specific value independent of the other one. So you can probably guess we're just summing up all possible values of the other random variable. So here, the small letter x is just all possible values of xj prime, and we sum up the probabilities over like all of these x. And the resulting probability is called the marginal distribution of xj, only xj. Next, something that's kind of similar but different is called conditional distribution. So conditional distribution is basically given a specific value of the other random variable. What's the probability of this random variable taking on specific values? So here the formula is very simple. It's just both of them occurring at the same time divided by the thing that we are given. So it's basically joint distribution divided by the marginal distribution. And the marginal corresponds to the variable that's given. Okay, so I think without a specific example, these things are hard to understand. So let me actually give you a very simple example. I think I will give you another example during the lecture, but let's have something that's very simple. So first, let's suppose x1 is basically taking out values 0 and 1, and 1 means if you flip a coin, it's h, and 0 means it's t, tail, head or tail. So this is basically a coin. And suppose x2 is counting the number of heads if you flip 2 coins. So number of head for 2 coins. So it can take on values 0, 1, and 2. Let's say this x1 is our first coin. So they are actually related. It's not 3 different coins. So then we need to calculate the probability. In order to specify the joint distribution, we need 6 probabilities, both of them taking on values 0, both of them 1, and so on. So let's first look at physically what's going to happen. Like if we actually throw 2 coins, they can be HH. The first H occurs with probably half and the other H 2. So half times half is 1/4 of the time. And similarly, HT happens with 1/4 probability, and TH also 1/4, and TT again 1/4. So what is this? So this is probability of x1. So the first coin is tail, which is these 2, and also the total number of heads is 0, so it must be this. So this event is basically this 1/4, so I'll put 1/4 here. So here, this is the probability that the first coin is head, but there are no heads, so that's never going to happen, so I will put 0. And this is the number of head is 1, and the first one is tail, so it's the only possibility is this one here. So it's another quarter probability this is happening. I mean, these two happening at the same time. It's only in this situation, so it's 1/4. And for the same reason, this is 1/4 like this. And two coins, the first one is tail. I mean, two heads, the first one is tail. Now that's not possible. And the last one must be a quarter. Note that they sum up to 1. Okay, so these are basically the drawing probabilities. And if we want to find the marginal probability for x1, then we sum up different values of x2. So basically sum up over the columns. Summing 1/4, 1/4, 0 is a half. 0, quarter, quarter is a half. So this is our x1 marginal distribution. So in particular, probability x1 is 0 is a half, 1 is a half, which is like right. So it's only the first coin. And if we want the marginal for x2, then sum up over the rows, it's half, it's half. So basically the distribution of x2 is most likely to be that there's one head, which should be the case. And what else do we want? Maybe we want something like probability that the first one is a head, given that there are only one head. So what should we expect? I guess it's a half, but let's use the definition. So the definition is the probability of both of them occurring at the same time, which means x1 is 1, x2 is also 1, so it's this number, 1/4, divided by the probability, the marginal probability that only x2 is 1. x2 is 1, the marginal probability is this row, I mean this column. So when it's 1, it's a half. So divided by half. So actually, if you simplify this, it is a half. So it looks right. And let me try another one. Probability of x2 given, sorry, I don't even have the number. x2 is 1, given x1 is 1. So that's basically just the probability that the other coins had. So it should be a half as well. Let's try it. On the top, it should be 1/4. That's for the same reason they're happening at the same time. Divided by only x1 is 1. x1 is 1. Again, the marginal distribution, a half. So yes, it is indeed a half. So you can calculate all the other marginal, and actually we calculate all of them, all the other conditional distribution the same way. Okay. So next, we are going to build a network. So there will be a lot of notations. So we're going to simplify this. We don't want to write large x equal to small x every time. So sometimes I'll shorten it to just have the small x in case the small x is corresponding to the large x random variable, if it's kind of obvious. But if we write something like probability of 1, 1, it's not clear what's happening, because I don't know which x is 1, which x is another 1. So sometimes we'll have subscripts. So we'll have something like probability of x1, x2, and you can just understand them as probability of x1 variable taking on this particular value, and x2 taking on this particular value. But if I write 1, 1, if it's clear, we can see that this has x1 taking on 1 and x2 taking on 1 as well. But in case it's not very clear, I'm going to have subscripts. Okay, so now let's talk about how to build a network based on these probabilities. So a Bayesian network, some people call it a Bayesian network. I don't actually know how to pronounce this. I will just call it Bayesian network. And it's basically a directed acyclic graph that basically captures the relationship between the features. So we have a bunch of features, say x1, x2, and x3. We can actually have the label as one of the features, but we will not introduce the label first. By the end of this lecture, I will go back and introduce the label. But here, we'll just assume they are related, and they are not related in a way that's kind of a cycle. So when I draw an arrow or an edge, it means x1, this feature directly influences x2, the other feature. So if you think about what used to happen, we have like x1 influence y, x2 influence y, x3 also influence y. So that's basically what used to happen. Now we are assuming there are kind of relationship between these features as well. But we're not going to allow cycle like this because this does not make any sense. It cannot be, there cannot be a cycle. So that's why we want acyclic graph. So something like this is okay. So x1 is causing both x2 and x3, and x2 is also causing x3. And if there are no edges, it means these variables are not related. They are independent. Of course, we need to explain what statistical independence and conditional independence mean. So I will talk about this. So intuitively, independence should be kind of intuitive. It's just both of them happening at the same time. The probability is the same as the first one happening and the second one happening if you take the product. So that should be the intuitive definition of A, B being intuitive. B being independent, and there's an alternative definition that's also kind of intuitive. It's if you find the probability of A given B, conditioning on B happening, then it's because B is not related, so it's just probability of A. So both of these definitions are okay, and if we add a conditionally independent, it just means we are using the same expressions. We're just conditioning on C for all of them. So basically, given C, A and B are kind of independent. So that's what conditional independence means. So in a network, there are usually three kinds of configurations. So the first one, as the name suggests, it's a causal chain. So it's a chain, basically A causes B and B causes C. So suppose we have three features. So I will use the example that I will use in the next two parts. So let's say A is the event that there is a fire at home, and B is the event that there is an alarm, and C is the event that your neighbor is calling you. Then if there is a fire, it causes the alarm to sound. It may not cause the alarm to sound, like with a small probability that the alarm is broken. And if the alarm sounds, then there is a probability that your neighbor is going to call you. There is another probability that the neighbor just ignored it. But basically, these variables are related in the sense that one causes another. So kind of if there's a fire, it indirectly causes someone to call you, but it's not a direct relation. So A is not independent of C. So they are related, but they are only related because of this link B. So if we know B already, A should be conditionally independent of C. So given that the alarm sounded, then you know whether your neighbor calls is kind of not related to whether there's a fire, because we already know that the alarm sounded. Right? So if we know the alarm did not sound, then also your neighbor can call you for some other reason, and that probability is kind of independent with whether there's a fire or not. So these things are, so as I wrote here, once B is observed, A and C are independent. So that's, again, another definition, another way to explain what conditional independence means. Okay, so that's the first configuration. And the other configuration, is common cause. So you have the same cause that can cause two different things happening. So maybe there's an alarm, and it can cause your neighbor 1 to call you, and also it can cause your neighbor 2 to call you. So if we don't know whether there is an alarm, then these two are related. Right? So A again is not independent of C. So if there's an alarm, both of them may call you at the same time. So they are somehow related. If one person calls you, it's more likely that the other person will also call you. However, again, if we are given this alarm, if we know the alarm sounded, then the probability that the one neighbor calls you and the probability that the other neighbor calls you is kind of independent. And it's same whether there is alarm or not. So in the case that there is no alarm, of course they call you for different reasons. So of course this is completely independent. So basically, if we are given, if B is observed, A and C are independent. So again, A is conditionally independent on C. So that'll be why we don't have say A, B, and C. We don't need a link between A and C because they are not directly related. Okay, and the last configuration is two things occurring that can cause the same thing. So B here would be alarm, and it may be caused by fire, or maybe your cat triggers the alarm for some reason. So these are two causes, and the probability that there's a fire and the probability that there is a cat problem originally seems they are independent, right? So A is independent of C, so that's why there's no link between A and C. However, A and C are not conditionally independent, because if we know if we know that the alarm is triggered, if it's triggered by the cat, most likely it's not triggered by a fire. Most likely there's no fire like occurring at the same time. And if fire triggers the alarm, most likely the cat does not trigger the alarm at the same time. Maybe, but well, so it's not a good example, but you can get what I mean. So once B is observed, once we know that there is an alarm, then A and C are kind of dependent. They're related somehow, because if one happens, most likely the other one does not happen. So here there's no link because of independence, not conditional independence. So these are the three main configurations, and after knowing this, we can actually reduce the number of probabilities that we need to store to save space. So here, if we have, say, m variables with k edges, then there are 2 to the power m joint probability to store. I'll actually give you an example. If we only store the conditional probabilities, and again, I will explain how to go back and figure out the joint probabilities later, we only need to store less than 4m number of conditional probabilities. And as I said, I will talk about how to figure out joint based on conditional. Okay, so let's combine the three configurations and actually draw our first Bayesian network. So there are two causes. One is fire and the other one is cat. And both of them can trigger an alarm. And if there's alarm, your neighbor number 1, Nick, may call you, or your neighbor number 2, Happy, may call you. So I know for Marvel fans, after you hear the name Happy, you know like completely what the story is. So for the people who are not familiar or have not watched the movie Spider-Man Far From Home, let me explain this again in terms of that movie. So let's use some images so that's easy to see. So first, there may be a fire, like this fire, actually a fire monster, but in any case, that may happen. That in that case, it will trigger alarm, obviously. And then there may be a cat problem. So that's our cat. So again, for Marvel fans, please don't complain that this is not a cat. This is not a cat. So I will put in the bracket. This can be a flirkin. Hopefully I did not spell this incorrectly. So it's basically an alien creature that looks like a cat. But in any case, the cat may also trigger the alarm. And then next, Nick Fury, him may call you. So that's this variable. And the last one, Happy, he may call you as well. Okay, so that's basically our story here. And let's move on to actually talking about probability again. So here, what kind of probability do we need to specify in order to specify the joint distribution? Let me see. So F, C, A, and N, and H. So in order to specify this, we need the probability, for example, all of them are 0. So there's no fire, no cat. I mean, cat does not trigger the alarm. And no alarm. Nick did not call, and Happy did not call. So that's the first one. And you can guess the next one is there's a fire, but no one is responding to any of these. And then the next one is there's a cat problem, and the alarm did not sound. And similarly, you can say both of them are happening and nothing is notifying me. That's the scariest situation. But there are lots of these. How many of these are there? So each variable can take on 2 values. So there are 5 variables. So 2 to the power 5. There are 32 probabilities to store. Actually, you can only store like 31 because the other one is just 1 minus all of the other ones, but it's basically the same. Okay, so then next, if we only store the conditional probabilities, how many do we need to store? So every time writing down like 0 and 1, it's kind of very tired. So I'll just write either that variable or not that variable. So for example, we can say the probability of F and probability of not F. So there's a fire and there's no fire. They're related. So if we store this number, this is just 1 minus that, so we don't need the other one. And then we also need C, because they are not conditioning on anything, so we don't need the conditional probabilities. And for A, we need the probability the alarm sounded if there's a fire and there's a cat problem at the same time. And we also need A given no fire, but there's a cat problem, and fire and no cat. And lastly, the probability that the alarm is triggered when nothing happened. So broken alarm. So do we need the not alarm ones? So for example, do we need probability of not alarm given fire and cat, which is the most dangerous situation? No, because these two sum up to 1. Right? Given F and C, it's either alarm or no alarm, so these sum up to 1, so it's okay. So we don't need that. Okay, and next, probability of Nick calling me given there's alarm. Probability of Nick calling me given there are no alarms. Are these sum up to 1? I guess no. So this is when alarm sounds, what's the probability of Nick calling me? The opposite is probability of not Nick and alarm. So not N, but A, given A. So these two do not sum up to 1, so we need both of them. And at the end, H given A and H given not A. So how many are there in total? So there are 10. There are 10 numbers you need to store versus there are 31. So here there are only 5 variables, so it's kind of, they are like similar. But imagine if you have 100 or 1,000 variables, then it's going to be a mess to store like 2 to the power that many probabilities. If you store these things, it will be a lot simpler. So on my website, there are actually many examples with more variables. So let's see here. So the first one is this one. You need to right click and let's open it in another window. So here it's a Bayesian network linking a lot of the variables that's related to suicide, I think. Yes, so some, for example, financial problems and emotional problems and illness, for example, all of them are related to suicide, and you store these conditional probabilities. So here it's basically a list of conditional probabilities that you need to store. It seems there are lots of variables, there are only a few numbers to store, so it looks great. And link number 2, let's see here. The conditional probabilities are not shown, but there's lots and lots of variables, and they're kind of related by some complicated Bayesian network. But again, if you store all the joint probabilities, it's going to be huge. And there's a website that contains lots and lots of this. It's called the Pathfinder, and it's basically a lot of yes. So the Pathfinder is just one Bayesian network. In here, there are lots and lots of other ones. So I think if you open this, it's I can't even see the variables, but it's related to some medical diagnosis as well. So there are large Bayesian networks built for specific problems. Okay, so in the next part of the lecture, we will talk about how to train these and how to evaluate these.